Welcome. In this lecture, we shall study the shear stress distribution for triangular sections of beams. Let's draw a triangular section of a beam and show the neutral axis. An arbitrary layer is denoted by an elemental strip of infinitesimal thickness del x at a distance of x from the apex of the triangle. Here, we consider the distance of the arbitrary layer from the apex instead of the neutral axis only because it is easier and more convenient for calculations. Let's call the width of the arbitrary layer as b at x if the width of the base is called as b and the depth as h. Now the width of the arbitrary layer is found to be linearly varying from the apex till the base of the triangle, and hence we can denote the width b at x distance from the apex as b times x over h by simple linear interpolation. Applying the general formula to find the shear stress at any arbitrary layer, we write the equation as tau is equal to s over b at x I times integral of b at x times dx times the distance from the neutral axis, that is 2/3 of h minus x. This is simplified gradually and the limits of 0 to x are applied to get the shear stress as s over 3I times h times x minus x squared. This shows that the shear stress varies parabolically with respect to the distance x from the apex of the triangle and is a maxima type of curve since the double derivative is negative. For maximum shear stress, we take the first derivative with respect to x and equate to 0, leading to x equal to h over 2, that is half the depth. This is different from the rectangular and circular sections where the maximum shear stress was found to be at the respective neutral axis. Inserting x is equal to h over 2, we get the maximum shear stress as 3 times s over bh. The average shear stress acting along the transverse or cross section of the triangular beam is given by s over a half of b times h. Hence, the ratio of maximum shear stress at half the depth and the average shear stress is found to be 3 over 2 or 1.5. Alternatively, the maximum shear stress equals 1.5 times the average shear stress. We draw the shear stress distribution diagram beside the triangular section and label the same with the value of the maximum shear stress. The shear stress at the neutral axis can be found by assuming the value of x equal to 2/3 of h. This gives a value of 8 over 3 times s over bh, that is 2.67 times s over bh. Now we may allocate some values to the parameters. For example, width b equal to 50 millimeters, depth h is equal to 50 millimeters, and maximum shear force S is equal to 100 kilonewtons. We hence get the maximum shear stress as 120 megapascals at half the depth and the shear stress at the neutral axis as 106.67 megapascals. In the next lecture, we shall solve problems based on shear stress in composite sections of beams and some even combining shear stress with bending stress in beams.